This video is on Young's double slit experiment for AP Physics 2. The first question involves drawing a diagram showing all of the symbols that you use in the AP Physics 2 equation and relating them back to the equation and the diagram. So the first lines we're drawing are the lines that go from the center of each slit to the first maxima, or bright spot, over on the screen. I'm also showing on there where the central maxima is. Now I've drawn in the distance between the center to the screen. The points from the center of each slit to the first maxima I'm calling lines L1 and L2. And then the angles they make with the line directly to the screen is theta. The distance between the two slits is D. Now I'm making this very, very small triangle at the base. I'm drawing a line perpendicular from L1 down to L2. And then I'm drawing the line of L2, and that's actually the distance that L2 is longer than L1. So this distance is the difference between the path lengths, L1 and L2, which is equal to m lambda. Now I've indicated on the drawing the distance y. Y is the distance between the central maximum and the next order maximum, or n order. So that one maximum in the center is our brightest spot in general, and then we would have the next order maximum. That would be y. Stated specifically, delta L is L2 minus L1, which is also m lambda. So what assumptions do we make? Well, first of all, theta 1 is equal to theta 2 is equal to theta 3. All the thetas are the same because they're similar triangles. That's true as long as we assume that L1 and L2 are parallel to each other. And again, that is an assumption. They're not totally parallel, but they're very, very close. There's a very small difference between the two. And of course, for the way we're solving it this year, for very small angles, which these are, sine theta is equal to the tangent of theta. That's another assumption we make in the way we're doing it. And finally, this brings us to not an assumption, but a statement of fact that the tangent of theta is equal to y over L, which means, with our assumption, the sine of theta is also equal to y over L. So now we've drawn the diagram. Now we actually have to solve the problem. And the problem states that we have a 500 line millimeter diffraction grating, and we're trying to find the wavelength, and the distance between the first and second maxima is 4 centimeters, and the distance to the screen is 1.15 meters. So now we're going to start to tackle the problem itself. The issue is we had a 500 line per millimeter diffraction grating. So how do we change that to a distance? Well, let's write down what we have. First, 500 lines per millimeter. Let's change those millimeters to meters. We'll worry about that in a minute. Let's go ahead and get all the others written down. We've got the y, we've got the L, and we're going to go ahead and draw a diagram of it again so we've got an idea of what we've got. Now we can see that if we just invert that, so we take millimeters per lines instead of lines per millimeter, and change, of course, millimeters to meters, then we get how many meters there are between the lines, which is 2 times 10 to the negative 6. Also realize that that 4 centimeters is between the first and second maxima, but it's the same because of symmetry between the 0 and 1 maxima also. And that 1.15 was that distance from the screen. So now we can go ahead and plug it into the equation. dyl equals ml. We're using y over L, the tangent, for the sine of theta, and we're using m equals 1. After we get all that written down, it's just a matter of plugging and chugging. And here we have our numbers plugged in and our final answer coming up.